Hello, class. This is our project for hydraulics. Uh, we are going to be explaining differential pressure flow meters. We are students at the University of Akron. This is Group 1. I'm Adrian Bivens,
Shariel Harvey.
and we'll be explaining about differential pressure meters. Hello, class. We've presented you with a handout. We're going to be going over the primary types and secondary types of our DP Flowmeter video project. We've provided the handout with pictures, pros and cons, applications, and descriptions. Towards the end of the video, we're going to explain how DP Flowmeters relate to Bernoulli's equation. If you guys need to take extra notes that are provided in the video and not in the handout, then please do. And we'll be giving clues on the exam questions that we provided.
Now we'll go over the basic elements in the handouts. Basically, DP flow meters have two different measurement points, one before and one after the cross-section of the flow to give a correct reading. Usually, different fluids flow through pipes with different properties. Something must measure the input of the fluid to ensure that they mix properly and not too rich or too lean.
Now we'll explain how it works. The differential pressure flow meter usually consists of two main elements. The primary element is the physical restriction, which causes a difference in pressure between the upstream and downstream pressure taps as flow increases. The secondary element is the part of the flow meter that measures the differential pressure drop.
Well, the flow rate is proportional to the square root of the differential pressure. This basic principle of differential pressure flow meters is based upon Bernoulli's equation. Overall, DP flow meters are mostly used in industrial applications.
Next, we will explain how the different primary elements work independently. Orifice plates are the most common type of primary element for DP flow meters. Most common orifice plate is concentric sharp edge orifice plate, which is shown in the picture on your handout, the one furthest to the left of the three types of plates. They are usually used in applications such as relatively clean liquids, gases, and low velocity vapor.
Second type is Venturi's tube. Venturi tubes consist of convergent cone section, cylindrical bore, and divergent cone section. The cylindrical bore restricts the flow, which results in a pressure drop. The flow rate is slowed down and causes the pressure to drop also. The upstream pressure tab and the downstream tab measures how this happens. This method is used in applications such as air, water, fiber, steam, gas, and chemical substance. Using this type consists in less pressure drop than the orifice plate type.
The third type of DP flow meter is flow nozzle. For flow nozzles, they have a smooth elliptical inlet which leads to a throat section with a sharp outlet. The throat restriction causes a pressure drop due to the cross-sectional area change. The flow nozzle is more efficient and has greater flow capacity when compared to most other differential pressure meters of the same size. This type can handle high velocity flow rates in steam applications, including dirty and abrasive fluids.
The fourth type is pitot tube. Pitot tubes measure the difference between the impact pressure in a flowing stream and static pressure at the tube wall. A U-bar averaging pitot tube takes multiple samples across a section of pipe or duct and it's averaging the differential pressure measured accounting for variation in flow across the section. It's used to measure clean liquids, gases, and steam. It can also be subject to clogging and sensitive to flow distribution.
Final type of DP flow meters is the V-cone. The V-cone is a differential pressure type flow meter that consists of a cone-shaped obstruction placed in the center of the pipe, which creates a differential pressure. Flow rate is calculated by measuring the difference between the pressure upstream of the cone at the pipe wall and the pressure downstream of the cone through its center. These are all types of the primary elements of DP flow meters. Now we will explain the secondary element of DP flow meters. The secondary element types usually consist of transmitters, gauges, manometers, or water columns. These all calculate flow rate of fluids. The DP transmitter is the most common. It usually has a local display and it could be wireless. So the summary of the types section, basically the primary elements are inside the pipe and the secondary elements is the gauge which reads what the primary element is doing in the pipe before and after. All types have in common restricting the flow in the pipe causing pressure drop.
Now we are at the important part, which is how we apply the Bernoulli's equations to our topic, the differential pressure flow meter. But before we go deep in that, Bernoulli's equations represent energy transmission. Also, it's helpful for us as engineers because it's well-defined equations, and it actually helps us finding what's going on inside any of flow that we need to measure. So I have right here the formula for Bernoulli's equation in heads, but it's applying for 1 point. I got here pressure over density, which is all over overall it's the potential energy. Here I have half of velocity squared, which is a kinetic energy, and here I have gravity multiplies it, which is static energy equal to a constant. Using that, I can came up with the differential pressure and how that we're gonna see it now. So I'm gonna bring this equation down here. So pressure over density plus half of velocity squared plus g, which is the gravity, equal all to the constant. But we need like to do it in 2 points, so let me fix the equations first. So I'm gonna multiply density in all these sizes, which density will cancel here, and I'll have density here and here. Applying this to 2 points will bring me to pressure 1 plus half of density velocity 1 squared plus density gravity 1. And the same will be applied for the second. Pressure 2 plus half of density velocity 2 squared plus density gravity c second all squared. Now I'm gonna find the differential pressure, so I'll move the P1 there and this one there. But before we do the movement thing, I want to mention that we are working on a steady state situation, and we considering that there is no difference in height, so these basically will cancel each other, because for the density when it's in steady state uncompressible, which means the density for inlet will be equal to the outlet, so no need, basically they cancel each other. Now saying P2 negative P1 equal the half of density P2 square negative this other half density P1 square, which all these lead to differential pressure. This is like how we came up using Bernoulli's equations to end up with our topic differential pressure. right here we have the flow rate, which is a big Q1 equal big Q2. The density cancel each other. As we said, we work in compressible situation. And maybe the picture there will help where is the flow cones and how it works there. This is basically working more accurate for the flow rate by adding the area on it, because as you see in the pictures, you might have difference by diameter or something, so you will be using this for flow to get like more accurate results. That's it for the Bernoulli's equation and how it applies to our topic.